Remember on Friday we're going to have a quiz over this last couple of stuff. This is the last section we're going to do in this chapter. And we're talking about E. E has to do with logarithms. We use it, it's just something we use a lot. It's like kind of like pi. It happens in math a lot. So E is an irrational number. Girls? E is an irrational number like pi. It just continues forever and ever and ever and ever without repeating. It just goes on and on and on and on. It says it's often referred to as the natural base, E, and it's found by using this weird looking formula. Basically what this is saying is the limit as n goes to infinity. So n is going to go on forever and ever and ever and ever, and it's about 2.7. In order to figure out what this is, we take 1 plus 1 over 1 times 1 plus 1 over 2 times 1 plus 1 over 1 times 2 times 3, and so on and so on and so on and so on. 3 times 4. Forever and ever and ever and ever. And that's how they get to E. It goes on forever and ever and ever and ever. But usually, we just round it to 2.71828. Is there a question?
I mean, no.
Give you one. Sorry. Alright, so an exponential function with a base E is called a natural base function. It's used to model continuous exponential functions. So continuous exponential growth and decay. Continuous exponential growth and continuous exponential decay. Notice that the functions are really, really similar. The only thing that's different is the exponent x is positive when it's growth and negative when it's decay. That's the only thing that's different. Okay, so the inverse of a natural base exponential function is called the natural log or natural logarithm. Natural logarithm. Okay, so this logarithm we can write it like we normally see, where we have a log. And in this case, instead of a base 10, like we're working with the common logs, it's a base E. So we can have log base E with an actual E in there, but most times they abbreviate it as Ln, which I don't know why they don't go like in L for natural logarithm, but they go Ln. That's just a second one. Most times the books have it as a lowercase l in, but I always write it as a capital L just so I know that it's an L and not a 1. But yeah. So natural log, you can write it as Ln or log base E. Since you can write it equivalent base E exponential function for a natural logarithm equation by using the fact that the natural log x is equal to the log E base E of x. Questions so far, thanks?
Yes.
It will make sense when you do it.
Work some problems out.
We can work some problems there. Alright, so it asks us to write it in logarithm form. So basically we're doing exactly like we did before. So we're going to say log, what's our base? B of B equals. Alright, how are we going to do B? How would you write it?
Log E of B L X equals 5.
Okay, instead of writing log E, we could also write Ln. So I could write this as Ln A equals X and Ln X equals natural log. Okay, questions so far? Alright, let's go on. It says Because you can also write equivalent natural logarithmic equation for natural base e exponential function. In other words, we can just go backwards. So then it asks us to write it in exponential form. So in other words, just reverse what we just did. So in this case, I would rewrite, and I think, well, natural log of x means log of base e of x is about 0.7741. So how can we write it as an exponential form? Okay, what's our base? E. What's our exponent?
0.774.
And it's equal to? That's what we do. Okay, so if we're looking at B, I would first think, okay, natural log means log base E of 10 equals x. When I get exponential form, what's our base?
EX, e to the x equals 10.
Okay, can we move on? Does this make sense so far? Okay. Okay, so all the properties of the logarithm that we learned also apply to natural logs. Whatever you're doing with the calculator, you can put it down. Alright, so all the properties that we learned before, like if we are adding like log base 10 of 5 plus log base 10 of 7, what can we do to rewrite it so we have one log? Right, because we would multiply them together. 5 times 7 would be 35. So all the properties that we've done before like this also work with natural logs. Okay, so if I'm looking at A, they ask us to write it with a single logarithm. That means they only want to see one log. Okay? What I would do first is I would say, well, we've got this 3 on the outside with this one, and I only want to have a coefficient of 1. So how can I rewrite this part on the left so I don't have a 3 as a coefficient?
ln 1000.
Right, because we can take this 3 and put it back as an exponent of a 10. So we'll have natural log 10 to the third minus natural log 8. And then since I'm subtracting the logarithms, how can I write it so we have 1? Divide. So we have natural log of 10 to the third over 8, which 10 to the third is it 1,000?
Yes.
8. 125? Okay, now normally when we see something like this, since we can take 125, and I know that it is I can take out a perfect square, I can break it down. How can I rewrite 125 so that we have an exponent?
5 to 40.
No, I don't want E in there. Go back over here, 5 to something. 5 squared times 25 is 5 to the third. Look there. And then we want to take this 3 and bring it back on the outside. So we'll have 3 times natural log of
Why is it L? Why is it 125?
because you just can't, you always have to bring out the exponents. Right. Alright, let's try B. The same idea as what we did before, except with instead of log base 10, we're working with natural logs. Alright, what are we going to do first on B?
Coefficient into the.
Yep, get this coefficient and put it as an exponent. So we'll have natural log of 40 plus natural log of half squared plus natural log of x. Well, what's a half squared?
It's 1/4.
It is 1/4, so I'm just going to rewrite 1/4. Alright, we only want one logarithm. We don't have any more coefficients, so now we can put stuff together. How can we put them together?
Put the first two together.
Right. We can actually just put it all together at once. So since we are adding, that means I can multiply to put the them together. So the natural log of 40 times the 4 times x.
Just 10x.
Okay, now in this case, can I write 10 somehow as some number with an exponent?
So how did you get 1/4?
Because I put the 2 squared, half squared.
Oh, okay.
And no, there is no way I can write 10 with some kind of exponent. So in this case, that would be right. Do we need to do another example, or can we move on? Good? Okay. Because the natural base and the natural log are inverse functions, they can be used to undo, because it's like multiplication, division, they undo each other, or eliminate each other. Eliminate. So we get rid of, or can cancel them out. Alright, so in this case, if I was looking at this thing, I know that e to a natural log cancel each other out, so I would just be left with x. Over here, natural log and e again cancel each other out, so I'm just left with x. It's like multiplying by 5 and dividing by 5. It doesn't change my number. They cancel each other out.
So it's both just equal.
Yep. And so the equations and inequalities involving base e are easier to solve by using natural logarithms rather than using the common, meaning the logs of base 10, because the natural log of e is equal to 1. That's why they cancel each other out. They're gone. Okay, so when I'm looking at something like this and I'm solving, when I have an e in here, I want to get this by itself. So I would treat e to the negative 2x as one whole unit. I cannot break it apart. Write this for a second. Okay, I want to get it by itself. Think about it as if this said 4y minus 5 equals 3. Okay, I want to get it by itself.
Plus 5.
So we add 5. Okay, so our first goal is to get the e to whatever power by itself, which is what we've done. Okay? Once e is by itself, one side of the equation, then in order to get rid of it, I'm going to take the natural log of both sides. When you take the natural log of one side, you have to do it on the other.
Otherwise, you multiply the natural log.
Kind of like multiply the natural log.
So you have to add the ln's.
Yep. We're taking natural log of both sides.
So it just equals the natural log of 2.
Yeah, because the natural log of and the e's cancel on the left side. So we'll be left with negative 2x equals natural log of 2. Doesn't cancel on the right side because there's no e to get rid of it. So now I can get x by itself by just dividing by negative 2. Then,
Where does the e go?
the e cancels with the natural log here. They're gone. So we're just left with the x bar.
Can you have a negative?
We can add a negative. That's okay. And then plug this into your calculator. I want you to find on your calculator, there will be an LN in there, and usually above it, like in the shift or the second key, will be your E or vice versa. I want you to find it on your calculator. Depending on your calculator, you may have to push 2 natural logs. Sometimes you'll go natural log 2.
Oh, so it's not, but you have to add the ln.
Oh, here it is.
Yes, you have to write the LN. Or no.
Oh, oh, they're so funny.
Wait, what did I understand?
It's funny.
Of course.
My subsection of it's a long.
Okay, got it? Awesome. So you guys know how to find it on your calculator?
Subsection.
Alright, so what is next week in this case?
Negative 0.346.
You're right.
You
And
want
again, round to the nearest 10,000, so that means 10, or not 10 places, 4 places. 10 would be not a lot.
Oh, 10 places.
10 places.
I don't think my calculator has.
And I know that we talked about like with the regular logs, like the log, LOG log, you couldn't have a natural or a regular log of a negative number, but in this case we're working with E, negatives are fine. There's no problem with those. Questions on what we just done? They're really simple. Not much. Okay, let's try B. What's our first goal? What do we need to get first? On B, what do we need to do first? Yep, we're going to want to get B by. So I heard at 12, you're right. Okay, then what?
And then multiply by ln.
Good. You don't really say multiply by the natural log, you say take the natural log of both sides. But yes. Take the natural log of both sides. What happens on the left? They cancel. We're just left with 4x equals, oops, natural log of 5.
This is a lot better than that.
Then what do you get?
Wait. What cancels out?
The e and the natural log. They cancel each other out, so we're just left with less. So what is x about?
I got 0.424.
For what?
4024.
4 Seems right. Yep, that's what I got. All right, do you want to do C or do you want to move on?
Move on.
Move on. Okay. All right, just like the natural logarithms that we use to eliminate the e, we can also use the e to get rid of the natural log. All right? So, in this case, when we have a natural log of something, we're going to work it just like we did before. Where our first goal is to get the natural log of whatever by itself. Treat it like a y, so it's like we have 3y equals 24. Okay? It's one unit, we cannot break it apart at this point. So we want to get it by itself. What are we going to do?
Divide by 3.
Divide by 3. So natural log 4x equals. Alright, so now once the natural log of whatever is by itself, then we're going to do e in here. Yeah. Alright, so in this case, when we're taking the e of both sides, you can't really take the e. You're going to make these both exponents on an e. So I would write it as e to the natural log 4x equals e to the 8.
So you want me to make the 8 in?
Okay.
Those cases.
Yes, over here on the left, e to the natural log again cancel out. So we're left with 4x equals e to the 8. And again, x by itself, so divided by 4. So then we plug it into your calculator. Make sure you're using e. You'll probably have to push a second or a shift key to get there.
I got 745.
Yes.
Yep. You got it. And it says round to the nearest 10,000, so you want 4 places again. 45.2, so 89.5.
The letters first, I mean the numbers.
Yeah.
It is on your calculator.
Divide by 4.
Yep. Wait a second. Wait a second. How do you do that again? Your calculator, you're going to have to put the number first. So it's going to be e first, and then second. And then divide by.
Because you're an expert.
Alright, let's look at B. B is a little bit different, but pretty much the same idea. Okay, we're looking at B. What are we going to do?
Would you multiply by 4 on each side, get rid of that exponent?
No, you can't do it that way, because we're not working with a log of something. Okay. Must experience. Yeah, I guess I'm done. Alright, well let me ask you this. Is the natural log by itself?
Distribute it.
Don't distribute. No. Is it by itself? Yeah. So we can already just take e to the.
Oh, dang it.
To try to make it harder than you have to here. Okay, so then e and the natural log cancel. And we've got x minus e to the fourth is less than e to the fourth. And we do what? How do we get rid of this? Fourth root.
Does it cancel?
It does. And on this one, since we've got a fourth root here, it just cancels. So we're left with just e. It'd be like e to the 1. Yeah. E to the 1.
Can we just do a project instead of final?
Please. I think I would
No,
die.
I
It's your last year.
Wait, so what?
What did we do last year?
You still got mine.
That was last year.
Yeah.
So,
We just have like another copy.
Josh, you must time. No cheers.
all right. Do we need to do another type of these problems, or can we go on to the last thing?
I think we are good.
You're good? Yes. Yep.
Yeah.
We're good.
Okay. Last thing. So we've talked about finding interest before. Normally when we do interest, it's compounded at a certain point in time, like every month or 4 times a year or something like that. There are also continuously compounding accounts. In this case, instead of just finding the interest like every month, like I said, it's found every single minute of every single second of every single. It's just continuous forever.
No one does
Why
that.
do they do that? Some makes
5 minutes.
they just keep
That's a
going.
good investment.
Yeah.
Was it like a 0.003 investment?
Well, yeah, I'm sure like every second is like a 0.00000. You know, but it's continuously compounded, so you're getting interest always.
I guess like 1 cent of interest.
It depends on how much is in your account and how much interest there is. All right, so if we're continuously compounding it, it looks exactly like we've done before, except in this case you don't have to worry about how many times it's compounded in a year. In this case, it's just always. So P again is principal, how we put in the amount originally. E to the R is our interest rate, and T is time, like we did before. All right. So example 6 says, when Angelina was born, her parents deposited $3,000 into a college savings account, paying 4% interest compounding continuously. Assuming there are no deposits or withdrawals from the account, what will be the balance after 10 years? All right. So, what are we looking for? A, P, R, or T? We're looking for A. What's our P? What's the principal amount? 3,000. E to the, what's our R?
0.04.
0.04 times T, which is 10. Alright, so then all you do is type in your calculator. I suggest you find E to the this, and then take it times 3,000, just so you don't get your calculator confused in what you're trying to get there.
Oh, so the E goes to the X.
Yes, E goes with the X. Oh, let's see. We should have $4,475.47.
Right.
Yep. And the last one says, how long will it take the balance to reach at least 10,000?
So you know what the A is.
Right, we know what the A is. Trying to figure out time. Yes. Okay, equals, our principal is still the 3,000. E to the, our rate is still the same. In this case, we're looking for time. I'm looking for t. It's not something you can just plug in your calculator right away. What should we do?
Divide by 2,000.
Good. Get the e by itself. Okay, so cancel, so 10 thirds. Alright. Now what?
Should we read the questions of this one?
Do the
Good. Take the natural log of both sides. Okay, so we got natural log of 10 over 3. What happens on the right side? Yep, they cancel, so we just have like there 4 times c.
Isn't it 0.004?
No,
It's 4%.
it's 4%. You just move the decimal.
Oh.
That was 0.04%. Alright, then type in your calculator. Make sure you put 10 thirds in parentheses just so you're taking the actual whole fraction. So, about how many years?
About 30.
About 30 years. As long as the interest rate stays the same. So, it would fluctuate. Alright.